7.1. Today we are going to be looking at solving systems of equations in two variables. First, we're going to determine if an ordered pair, 2, 3, is the solution to the system of equations. If it is the solution, that means that it will make both equations true. In the ordered pair, the x value is 2 and the y value is 3. So we are going to plug in these values into each equation to see if it makes a true statement. Checking the first equation, we're going to plug in 2 for x, and then we're going to plug in 3 for y. And I'm going to put a question mark above my equal sign because we're checking to see if it is true. Following order of operations on the left, we get 9, and then add 2 on the end, and it does equal 11. We also need to check and see if it makes the second equation true. This one also works. Because it makes both equations true, we say that 2, 3 is the solution to the system. If the x and the y value given in the ordered pair only made one of the equations true, or neither of the equations true, we would say that it was not the solution to the system. Let's talk about what it really means when we solve a system of equations. Take the same two equations that we saw on the previous page and put them onto a graph. We are looking for the point of intersection between the two lines, and the coordinates of this point we call the solution. We saw earlier that 2, 3 was the solution, and graphically this shows up as the point of intersection. In general, any point that falls on the line is going to be a solution to that line's equation. So there's infinite number of x and y values that make this blue equation true. Same for the red line. All of these points are xy values that make the red equation true. What's unique about the point of intersection is that this is an xy value that makes the blue equation true and the red equation true. And so it's one unique solution to our system. One way to solve systems of equations would be making a graph and finding the point of intersection, like we saw on the last page. But today we are going to focus on algebraic methods, other ways to still find the solution, the point of intersection, without actually making the graph. The first method we are going to look at today is called substitution. Notice how in our system we have the second equation, one of our variables is isolated, y equals, and it's equal to this expression 2x plus 7. We are going to take the 2x plus 7 from the bottom equation and substitute that in for the y variable in the top equation. Whenever we do a substitution, we always want to use parentheses for the quantity that's going inside of the other variable. So rewriting the top equation, we have 2x minus 3. Now remember, 3 was really being multiplied by y, but we're going to replace y with this bottom expression, 2x plus 7. Notice how we're keeping that in parentheses, is equal to negative 13. So the only part that's different from the original equation is that we've plugged in a different representation for the y variable. Notice how now we have an equation that's only in one variable. X is the only variable here, so this is going to allow us to solve our equation for x. We're going to continue solving like we normally would, so we're going to go ahead and distribute that -3 into our parentheses. And here we're going to combine like terms, add 21 to both sides, and divide both sides by -4. We find out x equals -2. Now we're not done yet. All we know is that the x value for the point of intersection is -2. We still need to figure out the y value. All we need to do for this last part is to take the x value that we got, -2, and plug that back into either one of the original equations to solve for y. In this case, it may be easier to plug it into the bottom equation because it's already in terms of the y equals. But if you plugged it into the top equation, you will still get the same answer. So altogether, we find out that our y value is 3. So we can go back over here to our point. X value is -2, y value is 3. And over here, we're always going to list our final answer, our solution, as an ordered pair, showing the x and y value. We're going to look at another problem that is solving using substitution. Unlike the last problem, neither one of our equations have a variable isolated. We do not see a y equals or an x equals. Sometimes we have to solve for a variable first before we can do our substitution. In this case, the easiest one to solve for would be to solve for x within that second equation. All we need to do to rearrange this is add 2y to both sides, and now we've created another version of that second equation. X equals 2y minus 3. Moving forward, we're going to continue to use the top equation and now the new version of the bottom equation. This time we're going to do a substitution for the x variable, unlike the last problem where we were doing it for y. Another name for x in this case is 2y minus 3. So we are going to plug that 2y minus 3 in for x back into the top equation. Use parentheses, always, whenever we're doing a substitution. Here we've got an equation, only one variable is y, so we're going to continue solving this like we normally would to get the y value for the point of intersection. So here we get y equals 4, and we have to plug that back in, as we did before, to get now the x value for the intersection point. Now we can plug this back into either one of the original equations, but the second one down here is going to be a little easier for us. So we'll go ahead and type in x equals 2 times 4. Oops, jumping ahead there. I had the 5 in my head for the answer. So x value for our point of intersection is 5. We're going to list our solution all together as an ordered pair, 5, 4. And when you get your solutions, you can always check your work, doing like what we did in the very first problem, plugging these into both equations to see if it makes both of them true. Next, we're going to look at another method for solving a system algebraically. This new method is called the elimination method, but is also sometimes referred to as the addition method or the combination method. In this next system, this elimination method is based on the fact that if we add the same thing to both sides of an equation, it's going to keep the equation true. So we're saying that 3x minus 2y is the same as 10. So if we add 3x minus 2y to the left side of the first equation, and if we add 10 to the right side of the first equation, that would really be adding the same thing to both sides. So we're going to draw a line underneath. I always like to put a plus sign in front over here, and we're just going to add down the columns. 3x plus 3x gives us 6x. 2y plus negative 2y is 0, so that cancels out. And on the other side, we have 24. What's nice about this elimination method is that we've eliminated one of our variables. We've got down to an equation with a single variable, 6x equals 24, divide both sides by 6, and we get x equals 4. That's the x value for the point of intersection. Now to get our y value, there's probably not an easier equation to plug it into. Either one is fine. Let's go ahead and just plug that x value into the top equation to solve for y. But you would still get the same answer if you had plugged it into the bottom equation. So it's minus 12 from both sides, divide both sides by 2, and we get that y is 1. Final answer, as in ordered pair, 4, 1. Sometimes we have to make some changes to one or both of our equations before we can do this elimination method. Notice right away that if we add together the x terms, 2x plus 3x is 5x, so that doesn't eliminate. Negative 7y plus y is negative 6y, so that doesn't eliminate either. We need to make some changes so that we can get one of our variables eliminated when we combine them. Because we have this negative 7y already at the top, if we can turn this bottom into a positive 7y, then we can get those two to cancel out. We're going to do that by multiplying everything in this bottom equation by positive 7. Remember that as long as we multiply the same side, or multiply both sides by the same thing, then it's okay. So let's actually rewrite off to the side here. The new equation that we get is going to be 21x, 7y, equals negative 140. Let's go ahead and rewrite that first equation so that we can get them stacked, one on top of the other again. Now we're ready to go to do our elimination method. So if we add together the x terms, we get 23x. Negative 7y plus y is 0, so that's going to cancel out. And negative 140 plus 25 gives us negative 115. Divide both sides by 23, and we get x equals negative 5. Again, we're going to take that x value, plug it back into either one of the original equations to get the y value. I chose the first equation, but if you plugged it into the second one, you should still get the same answer. And look, we happen to get that y is also negative 5. Final answer as an ordered pair, negative 5, negative 5. These are the different types of systems of equations we might encounter. The first situation, independent, that represents everything that we've seen so far. They are two different lines. There's only one solution, as we can see by only one intersection point. The second possibility is that the two lines given to us might be parallel. Remember that parallel lines have the same slope. They are never going to cross, meaning that there will be no solution because there's no intersection point. We call this one inconsistent. The last possibility we call a dependent system, and that's when the two equations actually represent the same line. So it's the same slope and the same y-intercept. There are really an infinite number of solutions because every single point on the line is a point of intersection that they share. It doesn't mean that every single point on the grid is a solution. It's just that there's an infinite number of solutions for the points that lie on those lines. Next, we're going to solve this system using any method. Based on the way it's set up, we have the x and the y terms together on the same side, and they're already kind of stacked up. Elimination will probably be the easiest method here. It's not that you can't do substitution. You could still solve for one of your variables, get x by itself or get y by itself. You should end up getting the same answer. I'm going to continue just using the elimination method. And we have a few options for what we can do. So we see right away that we have to change these equations so that we can get something to eliminate. It doesn't matter if you eliminate the x or the y. If we wanted to eliminate the x, we could turn one of these into positive 12 and the other one into negative 12. If we wanted to eliminate the y, we could turn one of them into positive 6 and the other into negative 6. The idea is that we're finding the least common multiple between the coefficients that are in front of the variables. I'm going to focus on the y variables, getting those eliminated. I'm going to take everything in the top equation and multiply that by positive 2, giving me a positive 6y. So altogether we have 12x plus 6y equals 24. For this bottom equation, I know that I need to turn that into a negative 6y. So what would we need to multiply everything by? That's right, we're going to multiply by negative 3. So we get negative 12x minus 6y is equal to positive 6. Now look at what happens when we try to eliminate. 12x minus 12x goes away. 6y minus 6y also goes away. So the only thing that we're left with is 0. Over here we have 0 equal to 30. What can we say about this statement? It's not true. It's never true. If we end up with a weird solution like this, a number equal to another number, it's not a true statement. This is representative of an inconsistent system. There is no solution. The other thing I want to show you on this problem, if we were to rewrite our equations in the y equals mx plus b format, the first equation turns into this. We rewrite the second equation and we get that. Notice how they have the same slope of negative 2, which indicates that they are parallel lines. So it makes sense that there will be no solution to this system. We're going to look at solving another system now using any method. Again, I would probably go for substitution, or not substitution, but elimination. I think it's going to be easier here. Let's look at maybe trying to eliminate the x's. We could turn one of them into positive 6x, and the other one could be negative 6x. Let's go ahead and multiply everything in that top equation by positive 2. So that's going to give us 6x minus 18y equals 36. Let's do the bottom equation by negative 3. So we get negative 6x plus 18y is negative 36. This is going to produce an interesting result. Everything eliminates on the left side, goes to 0, and the other side also goes to 0. So it's kind of an interesting result, but it is a statement that's true. It's always true that 0 will equal 0. And so this is representative of a dependent system where they are actually the same line. This is an infinite number of solutions. The way we're actually going to write our answer for this one, using what's called set builder notation, we're going to say all values of x and y such that 3x minus 9y equals 18. Or equivalently, using the second equation, we'll say all values of x and y such that 2x minus 6y equals 12. So this over here is actually how we're going to represent our answer if we end up with a dependent system. One final thing I want to show you with this system is that if we were to rewrite both equations in the y equals mx plus b form, in other words, solve for y, we see that we end up with the same exact equation, which means that they are the same line, so it makes sense that it's going to be a dependent system. Same slope, same y-intercept. Finally, we are going to finish up today by looking at a word problem. We are going to start by translating the information in the problem to two equations, making a system, and then we will solve our system. It says the sum of 3 times the first number twice the second number is 8. If the second number is subtracted from twice the first number, the result is 3. Find the two numbers. So let's let the variable x represent the first number and the variable y to represent the second number. Let's start by translating our first sentence into an equation. The sum of 3 times a first number and twice a second number is 8. 3 times our first number, 3x, plus 2 times the second number, 2y, is, when you see that word is in math, it means equals 8. Now let's look at the second sentence. If the second number is subtracted from twice the first number, the result is 3. So anytime we have subtraction, we're kind of going to make an opposite statement. So second number is being subtracted from twice the first number. Let's put twice the first number and then minus the second number. So it's kind of backwards. The second number is subtracted from twice the first number, and the result is 3. We've got our system set up. Now we can solve using substitution or elimination. I am going to use elimination for this one. I already have a 2y in the first equation. If we multiply everything in the bottom equation by 2, we can turn that into a negative 2y. So let's rewrite the first equation as it is and multiply everything in the bottom equation by 2. So we get 4x minus 2y equals 6. Adding our pieces together, we get 7x. The y's eliminate. 8 plus 6 is equal to 14. So x is 2. This tells us that our first number is 2. Now to find our second number, we can plug that back into either one of the original equations. I think I'm going to do the second equation this time. So we have 2 times 2 minus y is equal to 3. Subtract 4 from both sides. And if negative y is negative 1, then positive y is positive 1. So our two numbers, first number and second number, are 2 and 1. This is the end of my lesson on section 7.1, solving systems of linear equations in two variables.